Good morning, everyone. I'm Mohamed-Amine Babay, PhD student in renewable energy at University Sultan Slimane, Mellal. It's a pleasure to be with you at this conference, and I will thank you for this opportunity that you give me to present my work, modeling and simulation of PEM fuel cell using CFD model. Without delay, I will start by revealing to you my work plan, summary, introduction, modeling, simulation results, and conclusion. So the objective of this study is to numerical for three-dimensional non-isothermal computational fluid dynamics model of PEM fuel cell. Details analysis of the fuel cell performance under various operation conditions have been conducted and examined. As an introduction, energy issue currently cover two challenges. One is related to the risk of depletion of fossil and fossil resource. The other is environment. The source used today have finite reserve, both for fossil fuels like hydrocarbons, coals, and for fossil fuels, uranium. The fuel cell is therefore to missile link transforming chemical energy into electrical energy that can be handled with high efficiency. The fuel cell uses to redox reaction between hydrogen and oxygen to produce water, electricity, and heat. And we move to fundamentals of PEM fuel cell. Fuel cells are made of four major units like PEM, GDL, gas diffusion layer, catalyst layer, and bipolar plates. So the protons are conducted through the membrane to the cathode, but the electrons are forced to travel in external circuits because the membrane is electrically insulated. On the cathode catalyzed, oxygen molecule reacts with the electron and proton to form water, the only waste products in this type of fuel cell. The governance equation of the model. The main assumption adopted in the model are thermal equilibrium, membrane, catalyst layer. The mathematical model is composed of governance equation for the conservation of mass, momentum, species, energy, charge, and water transport into membrane. The condition. The GDL and the catalyst layer were surrounded by slab-sided plates and the inlet and outlet plane. So the boundary condition at the inlets and outlets check the no-slip condition for the velocity and the no-permeable condition for the species mass fraction. The Dirichlet condition is used at the inlet of the cathodic and anodic channels for the species height and mass conservation equation. The mass flow rates are considered constants at each channel. The Newman conditions are employed for all parameters at the interface fluid, solid to non-slip condition and zero species flow are considered. So for simulation results, forcible reaction gas and temperature distribution inside the fuel cell. It is figure 1, hydrogen molar fraction distribution into anode channel and GDL at base case condition. Into GDL, the hydrogen concentration under the solid parts of the bipolar plates is lower than that under the low parts channel. So we have two figure 1 and 2. As we said, the concentration of hydrogen into catalyst layer is balanced by the quantity of hydrogen received from the flow channel through to diffusion layer due to concentration gradient, which lowers the quantity of hydrogen consumed. The, the second figure hydrogen molar fraction distribution in three dimensions for the anode catalyst layer. The detailed distribution of molar concentration and hydrogen consumption are shown in figure 1 and 2. The hydrogen concentration decrease from two inlets to two outlets of the channel due to the consumption of reaction into catalyst layer. Distribution of hydrogen and oxygen. The molar oxygen concentration at catalyst layer is shown in figure 3 and 4. So at a low current density, the oxygen consumption rate is low enough not to cause diffusive limitation, whereas at high current density, the concentration of oxygen under the land area has already reached near zero value and cannot further decrease. The consumption field of oxygen and hydrogen are similar, except that the hydrogen consumption is twice as large as the oxygen consumption. The temperature distribution inside the fuel cell for this current density is shown in figure 5 and 6. The maximum temperature occurs where the electrochemical activity is high, which is near to cathode side inlet area. However, the temperature increase for low current density is small, only 1. Conclusion: this work presents a simulation study of a fuel cell single cell by analyzing two physical phenomena into cell core, the transport of charge into electrode and of ions of the membrane represented by the conservation equation to cell voltage being as boundary condition. The gas transport into diffusion layer consists of stable Maxwell diffusion, binary diffusion of the gas mixture, and convection due to pressure gradient. This model describes the reaction layer taking into account the dimension of the agglomerates that structure this layer. And thank you for attention.